So we can now see how the model of the universe and how we have perceived it has changed over a very long time, starting with Aristotle being refined by Galileo and then refined even further to Kepler. All of these people were able to describe how the universe behaves from their point of view with the available data, but none of them were actually able to explain why the universe behaves how it does. And one of the things that probably annoyed Kepler so much is the fact that while he did come up with a model of the universe that was much better predicting where everything was going to be, he still didn't have an explanation on why this is. I found something that is in direct violation to what I believe to be true. I have all the evidence to show that my belief structure was wrong, but I don't know why. So then, much later on, we have Newton. And Newton comes up with an explanation on why the planets behave the way that they do. Not how. That was just direct, what are they doing? That was already done by Kepler, but why? And to do that, he was actually able to make a connection between gravity and the rest of the universe. Remember, Newton did not discover gravity. People knew about gravity long before him. But what he did do was able to make a connection that most people were not able to think of. By observing cannonballs, he observed that when a cannonball was fired, it traveled as a projectile. And the faster you fired the cannonball, the longer the range was, making the arc larger and larger. But then he was able to extrapolate that, saying, well, we're on a round planet, or really a spherical planet. And if I was to take a ball and drop a ball, it would go straight down. If I was to throw a ball, it would be a projectile. If I was to throw the ball even farther, the range would increase. And if I was to throw the ball fast enough, then the arc of the projectile path could mimic that of the Earth, and the object would return to its starting spot and repeat the cycle. The object would orbit the Earth the way the moon does, and the way the moon orbits the sun. This means that the force that makes all planets move in the solar system, and thus the universe, is actually gravity. And since gravity is a force, he could then apply his three laws of motion to explain all the motion in the universe. Because gravity is a force playing on objects in space, those objects in space will in fact change their speed and or direction as we see planets do around the sun and the moons do around the planets. Based off his second law of motion, if we were to know their accelerations or masses, we could calculate the force, or if we knew the force, we could then use the acceleration to calculate mass, and so we'd be able to come up with some measurements of the objects in the universe, even though we've never been there physically. Basically, what he now allows us to do is to realize that we are one with the universe, and we now have a law of universality, where the physical laws that take place in one spot of the universe take place in all spots in the universe. So to understand what's going on off in deep space, we don't have to go all too far to understand the basic laws. That would be the same laws that apply over here on Earth itself. And to understand the motion of all things in the universe, you just really have to understand the motion of a falling object, because everything in space is basically falling to one another. And that is a key concept, that objects that are orbiting one another are actually objects that are falling towards each other, which means all the properties of a falling object, such as acceleration of gravity being independent of the object's mass experiencing the accelerations, must be in play. And the reason for that is simply because of Newton's second law of motion. If gravity is the net force acting on the object, then that net force must equal the mass of that object times the acceleration due to gravity. And the acceleration of gravity for that object must equal the gravitational force divided by the mass of that object. But since gravity depends on the amount of mass the object has, The more mass you have, the more force you have pulling on you, which would suggest falling faster. But since mass is resistance to forces, the more mass I also have more inertia, more resistance to forces. So the increase in force and the increase in resistance to force balance out to the same acceleration. We've made this analogy before. It's the same thing as a heavyweight fight versus a lightweight fight. The reality is both competitions are equally difficult for the opponents. In the heavyweight fight, you have people who are way more massive and they have way more muscle mass. That means they often hit harder, but they also have a higher resistance to the punch. While in the lighter weight matches, you have people with less muscle mass, which would then infer that they don't hit quite as hard, but their bodies also have less mass, so they have less resistance to those punches, making each fight equally hard for their opponents. Since an orbiting object is moving in a circular path, even if it's elliptical, it is still circular in its nature, we will have the centripetal acceleration. The centripetal acceleration is always equal to the tangential speed of the object divided by its radius, or the angular speed of that object squared times the radius. And since gravity is the net force acting on you in an orbit, the centripetal acceleration on the object is equal to the gravitational acceleration. This means the gravitational acceleration an object is experiencing orbiting a planet can simply be found by finding the centripetal acceleration, the tangential orbital speed squared over the radius, or the angular orbital speed squared times the radius. For an ellipse, the math becomes a little bit more involved just because both the speeds and the radius are changing. So you have different centripetal accelerations at all points along the ellipse. We're only going to look at circles in this case because the math is just simpler.